Uh, right. Right. So I hope you enjoyed the last lecture that Robertino gave about web programming. I must also still watch it, but I hope that was a lot of fun. So in principle, that concludes the Haskell part of this course. So now we want to turn towards Cardano smart contracts. But of course, I mean, one of the reasons we taught Haskell in the first place is that it helps a lot to know Haskell in order to do smart contracts on Cardano. And the plan is that this week we'll talk about Marlowe. I mean, Cardano offers in principle two smart contract languages at the moment. One is called Plutus, one is called Marlowe. And Marlowe is much simpler and also like specialized to financial contracts. So I want to talk about that this week, and then for the following, let's say 2 weeks, talk about Plutus. And the idea is that today I will mostly not talk about Cardano specifically, but just about the Marlowe language. And then on Thursday, we'll like become more practical and actually run contracts on the Cardano blockchain itself, or rather, at least the test net. I mean, we don't want to like use real money, of course. Okay, so Marlowe. But before we get to Marlowe, I want to talk about DSLs, domain-specific languages. And for that, allow me to switch to code. And before we get into this, let me just 1 second. Remind you of an example we had in some weeks ago where we talked about free monads. But I must just give me a second, sorry. I think that was lecture 19. Let me just briefly copy this. Sorry. I just want to like recreate that example, or at least a variation of this example. I always forget whether it's yeah, GHT options, but a colon is missing. Okay. Just check the example quickly. Was it right? Exactly. So this free monads ad hoc. Just want to I think we don't need this. Must remove this second cabal file. Right. And I think this here uses a different version of base, but it doesn't matter. It shouldn't matter. Okay. Good. That seems to work. What's this? All right. actually this one I want, sorry. And the rest I think I don't need. Sorry, almost there. Right. Let's see whether it still builds. Okay, right. So because first, before we talk about Marlowe, I want to talk about DLLs. Why is there an error? Probably must reload it. Okay, so this seems to be fine now. Let me just open my REPL. Okay, so I want to talk about DSLs. And unfortunately, there are no slides for this lecture because it's like a new part. So yes, so no slides. So DSL, domain specific language. And I mean, Haskell, of course, I think it's a beautiful language and you can do everything with it. I mean, we saw, or you saw last Thursday that you can do web programming, and we had this chat server. And I mean, you can also do databases and graphics and whatever you can think of, music. So it's a general purpose programming language. But one thing Haskell is particularly good at is modeling other languages. So a lot of like new languages, experimental languages are first implemented in Haskell, because Haskell is really good at basically implementing other languages. And there are various techniques how you can do that and various flavors of such languages. But in principle, so this, for example, this old example from the Three Monads lecture was an example of such a DSL, domain-specific language, where the domain, I mean, was like simple arithmetic expressions. And you can very easily in Haskell write a data type like that. And that's relevant for today's and lecture and the lecture on Thursday, because Marlowe is also a domain-specific language, which is or can be implemented in Haskell. So in a very similar form. So first, I want to just remind you, so now I deleted everything else. I mean, we had various implementations, but maybe I can just do that quickly. Let me just remember. So we had like int expressions. You could add expressions, you could divide expressions. They could look up variables from an environment and sequence expressions and assign a value to a variable. So maybe just as a brief reminder, we can write an evaluator again. And that is also something I mentioned first when we talked about parsing. A type like that has no meaning by itself. I mean, obviously the names are suggestive. So add obviously is supposed to mean addition or division and so on. But I mean, it's just names. It could be, I mean, it has no meaning by itself. So the way you give it meaning is with so-called semantic functions, which take. Is there a question? Or?
No, I think someone. Okay, right.
Okay, sorry. So I mean, so basically a type like expr has no meaning by itself. It gets meaning by so-called semantic functions that go from expression to something. And one such example was evaluation. And so given a value of this type, we can try to evaluate that to, for example, an int. And maybe I can just briefly do that again. So, I mean, we slowly extended this type. We started with just lit and add or something, and then added other constructs. And in the end, we ended up with this. And in parallel, basically, we also had a monad that we added features to accommodate all the things we needed. So maybe I can just cut all those intermediate steps, and just as a reminder of monad transformers. So let me just import control monad state and accept. I mean, this lecture is not about monads. It's I don't know why this now doesn't work, but for some reason stylish Haskell doesn't work anyway. Maybe because this uses a different version of THT. Doesn't matter. Right. So oh yeah, and this map also, oh yeah, that's imported. Fine. So I think what we did, or something similar, what we did, so we defined a monad. And we need somehow exceptions, because we can, for example, divide by 0, or we can try to look up a variable that hasn't been defined. And we need state to keep track of the values of variables. So we can, for example, do except t. Then we need an exception type. And I know we had, so in principle, I think only two. It was slightly different when I gave this lecture, but now it doesn't matter. So let's do, call it whatever, expression exception. So what can go wrong? I mean, we can divide by 0, or we can try to use a variable that hasn't previously been defined. So maybe unknown variable, and that variable has a name. Sorry, just set the to 4. Okay. I think I just need show. Okay. So then one suitable monad would be except t, and the exception type is expression exception, and the underlining monad is state, and as state I need an environment, and then a. Just excuse me, just 1 second, please. Just give me 1 second. Okay, sorry about that. Why this that? Oh yeah, I forgot a T there. Okay, and then we can deriving functor, applicative, monad, monad error, expression exception, and monad state env. Need this generalized new type deriving extension to do this automatically. And okay, sorry, this. Okay, and this is a suitable monad to do this, I think. So let's do this. So we can write something like eval m, that given an expression, evaluates it in this monad. So it gives us an int in that monad. Okay, let's do this quickly. So if it's a literal, then the value is just that literal. If it's add, then I can just using applicative syntax, call eval recursively on X and Y, and then add the results. So now diff is a bit more interesting because X could be 0. So I can recursively try to evaluate the Y. And if that happens to be 0, then we throw in division by 0 exception. Sorry. And else we evaluate the X as well. Do this. And let me just see whether until now everything compiles. Yes. So now those three are missing that involve variables. So the var case okay, so now I need my state. So I can use get to get the state, and then I must just import this. So I can use map lookup to see whether that is defined. V off. So if it's not, then I can throw an exception. So in that case, it's unknown variable. The name is V. And if it has a value, then I can return that. What's still missing? Sequence is easy again. I simply evaluate the first, forget the result, and then do the second part. And finally, assignment, also quite simple. So I can evaluate the second part. Now modify my state with map insert VN, and then the overall result is this. Oh, and here I've forgotten eval M. Okay. Okay, and now finally, I mean, now I have this monadic thing, but probably I want to just a simple function. So I can do that as well. So I have eval, which takes an expression and gives me either an exception or an int. So I have this eval M. Maybe I should, my life would be simpler if I give this a name, get M or something, or run M. Sorry, so I have this expression. I can do eval M of that expression. This is now of type M int. I can do run M. Sorry. Again, sorry. Eval M expression. Run M of this. So this is now of this type, except T, blah, blah. And, I deleted too much, right? Okay, so now I can do run except t. And what do I get now? Let's see. Oh yeah, so it's not run except, it's run except t. Okay, and now I get something of type state env, either expression exception int. So I can do eval state of this. And as initial environment, I can use the empty environment. And now what do I have? Okay. So now, okay, now a run identity should do it. Okay, and that's that. As I said, basically just a repetition of what we did in that lecture. Here is still this example program. So I can try this now, eval program. I get a right 9, is that correct? I set x to 16, then I set x to x divided by 2, so now x is 8. And then I seek, and finally I add 1 to this. So 9 is correct. But if I change this here to a 0, for example, then I get a division by 0 error. Let me change it back. And if here, instead of looking for x, I'm looking for y, for example, I reload, then I get an unknown variable y error. Okay, so far so good. So I basically just, as I said, this was nothing new. I just replicated this part of the lecture. But back then, our emphasis was on monad transformers and on free monads. So this was an example of how to use, how to basically build custom monads to do things like this. So now I want to concentrate on the DSL aspect. So this is basically a mini language, domain-specific language, that allows us to, I mean, it's like a simple programming language. Right. I mean, it's a very simple programming language. So for example, it doesn't have conditionals and it doesn't have loops. All it has is these very simple expressions, so literals, addition, division, and then it has variables. So you can use variables and assign variables, and you can sequence expressions together. But that's also no loops, no conditionals, as I said, and very limited range of operations. Nevertheless, I mean, it's nice how easy you can do something like that in Haskell, and then you can work with it. So this eval here is an example of a semantic function that I mentioned before. So by defining a function like that, we basically give meaning to this data type and say this is what that means, how that relates to integers, or we basically give it a semantic, a meaning of how to interpret such a value of this type, program like this. Okay. Now we had this example where I changed this x to a y, and then I got this error. So it would be nice, maybe, I mean, if you want to implement an actual programming language, it would be nice if you could prevent such errors. So for example, never use a variable that hasn't been defined. If maybe at compile time, you could already detect such errors. And of course, in Haskell, normally you can. Things like that. I mean, in Haskell, you can't use variable that hasn't been assigned. But you could do, I mean, something very similar to, I mean, Haskell doesn't have like global variables anyway, but Haskell, for example, has these mvars. And what you could, and if you recall, an mvar is like a box that can contain value or not. And if you want to take the mvar, look at the value, then if there's a value inside, then you take it out and have it. But if there's nothing inside, you block. Your thread blocks until some other thread puts a value in. So, I mean, that can definitely also happen in Haskell, that basically you want to look at this mvar, but nobody had put anything into the box yet. So maybe your program, your thread blocks forever. So it would be nice if we could prevent things like that from ever happening, because that's like runtime errors that can be critical. But it's probably, or it's definitely impossible to do something like that for something like Haskell. And the reason has to do at least with Turing completeness. I don't know how strong your background is in computer science, if you know what that means. And I also don't want to define it. So, I mean, it's basically Turing completeness. So let me just say languages or programming languages. Languages that can do everything for which there is an algorithm. And of course, I don't tell you what an algorithm is, but intuitively it means if you have a recipe, an algorithm, a method to compute something, and you have a Turing complete language, then you can implement that algorithm in that language. And of course, almost all programming languages, or at least common programming languages, Java, C, Python, JavaScript, Haskell, are all Turing complete. It also means, in principle, what you can do in one Turing complete language, you can do in every other Turing complete language. It may be less efficient, or it may be much more verbose or inconvenient. I mean, obviously, programming languages differ from each other. Some things you can do very nicely in one, and it takes a lot of effort in another. But like theoretically, in principle, they're all equally powerful, especially if you ignore efficiency. So they are like powerful, and obviously we all want powerful stuff, but they also have disadvantages. So very powerful, but also disadvantages. So have you heard of the halting problem? It's not important if you haven't, but just as an example of like the dark side of Turing completeness is that they are so powerful that it is impossible or difficult to analyze them without actually executing them. And I mean, one famous example for that is the so-called halting problem. And the idea is, if you have a Turing complete language, I mean, there's a precise mathematical theorem, but roughly it means, sorry, roughly it means there can't be a program that inspects another program and says whether that other program will halt, stop, finish, whatever, or not. And I don't know how many of you have ever seen a proof of that. And I also don't want to give one now, but at least like a heuristic proof. So let's say we had something in Haskell. So let's say, assume we had something like this. So a Haskell function halts, which takes, just as an example, let's say an IO action int and returns a bool. And the idea is, given an arbitrary IO action, halts will return true if that IO action, when executed, will return an int without throwing an exception or entering an infinite loop. And returns false otherwise. So, I mean, a priori, it might be possible to write something like this. I mean, Haskell is a very cool language, very powerful, so maybe one could implement something like that. So halts takes a program, an IO action, and returns true if that action, if I execute it, would eventually give me an int. And if this IO action will throw an exception or maybe loop forever, this halts will return false. So, and the point is, it can't be something like halts can't exist. And there's a very pretty proof. And the idea I can give you now. So let's look at following program foo, which is of type IOInt. Okay, and foo does something clever. It it calls this magical halts function. So assuming we had something like that on itself. So foo has the right type. Foo is of type IOInt. So I can apply halts to it. And I mean, recursive functions in Haskell are fine. So in the definition of foo, I can of course refer to foo. Okay. And now we assume that we have this halts. And so if we had this halts and it worked as advertised, then halts foo will be true or false. And true is supposed to mean that foo will execute without an error and return int. So now I just do something like foo. Sorry. Then it's pure 42. Right, and this is now a contradiction, because so assuming we had this halts function, there was an implementation for that behaved like explained here. So given an arbitrary IOInt action, it returns true if that IOInt action, when executed, will at some point return an int. And it returns false if this IOInt action throws an exception or loops forever. So if we assume we had something like that, I could write down this foo function. Foo calls halts on itself, and then there are two cases that the result is true or false. And if it's true, that's supposed to mean that foo will return int without throwing an exception or going into an infinite loop. But I do an infinite loop here. And I mean, I could also throw an exception. And if it returns false, so that's supposed to mean that foo will throw an exception or enter an infinite loop, I return 42. So no matter what halts says, true or false, it's anyway, the foo does exactly the opposite of what, according to halts, it should do. So that's basically the idea of, I mean, of course, it's not a formal proof, but that's the idea how you can prove that the halting problem isn't, that it's unsolvable. So you can't write a program like halts. in Haskell. And the same proof basically works in any Turing complete language. So there's a formal mathematical proof for that. So, I mean, if you step back a bit, what does that mean? It means that for something as powerful as Haskell, you can't have useful like analysis tools like this Halts function that can look at a program in that language and then tell you useful things about it. I mean, this is of course not to say that there are no analysis tools in Turing complete languages. I mean, you do get linters, for example. I mean, there's HLint, which I mean always gives me these hints that I should whatever. I mean, if I do this, then I immediately get these squiggly blue lines, and it says redundant bracket. And that comes from HLint, which is a linter written in Haskell. So that is a program that inspects other Haskell programs for like problems or warnings. So of course it's possible also in a Turing complete language to write analysis tools that inspect programs written in that same language. But the halting problem or basically the fact that you can't solve the halting problem just shows us that there are limits. So for Turing complete language, there are certain analysis things you can't do. So certain things you can't decide, you can only decide by actually executing the programs. But the proof somehow uses the Turing completeness, or at least like consequence of it. So that means that even though normally for everyday languages, for general purpose programming languages, we strive for Turing completeness because we want this power, this flexibility that we can basically solve everything with it that can be solved with the program. It comes with disadvantages that it's hard to predict, or it can be hard to predict for a given program what it will do. And sometimes this is, I mean, or most of the time we accept that as just how the world works. But sometimes we really would like to have like assurance that, for example, a given program stops at some point, that it doesn't throw an exception. And one such example is blockchain, in particular finance. So, I mean, we're supposed to talk about Marlowe today. So Marlowe wants to make it easy to write financial smart contracts. So smart contracts running on the blockchain, on the Cardano blockchain, that make it easy to do financial contracts involving like transfer of money. And of course, as soon as money is involved, we would like to have like a high level of assurance that nothing can go wrong. And so we would like tools, maybe not like Halts, but similar, that I can give a Marlowe program, and then it can tell me like interesting facts about it. For example, that no money will forever be locked in the contract or similar things. And that is the reason why Marlowe is not Turing complete. So the designers of the language had to make a choice. And I mean, as I said, most programming languages are Turing complete, but the designers of Marlowe like purposefully decided to not create a Turing complete language because they wanted these static analysis tools. And just to give you an example, so this one is certainly not Turing complete. I mean, I can't prove that, or I don't want to prove that. But I just want to say that, so, I mean, normally one would think if something is not Turing complete, I mean, it lacks Turing completeness, then it's like an inferior language. But the point I'm trying to make is that even though that means you can't, I mean, you have less expressibility in your language, it can come with other advantages. For example, it can make static analysis possible or easier. And that's the trade-off that Marlowe makes. Just in order to demonstrate, so we had this program here, which is fine. And then when I change the X to a Y, then we know it at runtime it crashed with this unknown variable y error. And I mean, for expressions, I think it's easy to write analysis tools like that. So for example, let's just call it unknown variable. Expression pool. And I mean, here, I think I can, I mean, I haven't tried it, but I think I can easily write like such a helper function similar to this false thing now for expressions that takes an expression and analyzes it for certain problems or properties. So, I mean, it's again another semantic function, takes an expression and returns something. So let's go through all of these things again. So if it's a literal, then of course it doesn't contain an, or let me rename it, let me call it throws unknown variable to make it clearer what I want to do. So in this case, it doesn't, it's fine. What was the next? Sorry. Next was add, I think. So when would add throw an unknown variable error? Well, in order to evaluate it, I must evaluate x and y. So if either of these two throws an error, then add would also. So I can just call it recursively on both parts. And if one of those parts throws an error, then the whole thing does. I think the next thing was division, and that's the same as add. Although one could argue, I mean, if y doesn't throw an error and evaluates to 0, then I never have to evaluate x because I earlier already crash. So I could maybe let's be a bit more, let's call it can throw unknown. I mean, it's not important. Right. So as I said, I mean, maybe this one wouldn't throw if y already evaluates to 0, even if x throws it, because I will never get to that point. But let's not complicate our life with that. So now this is the interesting case, var. Right, and now I also see I have too little information, because I mean, what must I do now in the var case? Because it depends whether I mean, on my environment. So I need to somehow keep track of which variables I have already defined. So I think the easiest is if I also do sets. Okay. Can throw unknown variable. Okay. Right. And let me just rename it, because this will become a helper function. Um, and sorry, let me do it like this. So it will take as state a set of strings. That's the defined variables, and will return a bool. So then I must, in this case, it's pure. Sorry. False. Okay, in this case, it's so applicative style. So I had to do, should have done that from the beginning. Yeah. Same here, let's say. Okay, now the interesting, and let me just write the function I wanted originally to write. So without the prime and just returning a bool. So what do I do? I just eval state can throw the primed version on my expression, and as initial state, I again take the empty set of variable names. Okay, and now let's see. So this is the interesting case. So because here it depends, so I look up which variable names are defined at the moment. And then if the V is defined, then it's good. So it won't throw. Oh yeah, that's a stupid. So sorry, what I want is that VVS not. Right, so if V is defined, then it won't throw. And if it's not defined, it will throw. And finally, two cases, sequence and assign. Um, so that's basically the same as add and diff. So if one of the two throws, then the whole thing throws. And finally, can throw unknown variable prime assign Vx. So that's the second interesting case. Because it cannot, depends on whether X does. So let's first do this and throw prime X. So if that already can throw, then the whole thing can throw. So I can say if B, then pure true. But else, now this is interesting because now now the V is defined. So I must modify the state. Set insert V. And it cannot. What is the, okay, fine. No, whatever. Right. Anyway, not important. But okay, this is this now, and let's see whether it works. So can throw unknown variable on my original example program. It says false. So I won't get this error, but if I use this one, it recognizes there's a problem. And of course, I could also have like done it differently, that it doesn't just say true or false. I could also have returned, for example, the maybe string. Maybe let's do that quickly. So the variable that is would be nicer. Not that better. So instead of pure false, it's pure nothing. And then this is no longer right. So I somehow need a way to combine these two maybes. Right. Okay, and this is now a bit more complicated. So let me do it slowly again. So if set member VS, then pure nothing, else pure just V. Okay, here I combine again. So that just means if you recall the monoid instance on maybe, let's see, how does it work? I have just Haskell, just Kenya. Interesting.
You need to set the file. It's
Oh yeah,
el reloj.
yeah. Sorry, that's it. Oh, it combines them, which is not what I want. I mean, I actually wanted to that for example only the first, or it could give me a set of. Okay, fine. Maybe instead of maybe string, I can do a set of strings. So so it can give me all the unknown. Right, is that correct? Where's the maybe coming? Oh yeah, there. I mean, this is all not important, but I just want to get it right anyway. Okay. B is maybe not an appropriate name. It's called VS. Okay, and now I need to, so this is now a bit different, the logic. So I look up what can happen there. I insert the V and I just return the V's. Okay. Okay, fine. And now if I do this again on my example program, so there's no unknown variable in that program. But if I do it on the primed version, it finds the Y. Anyway, the whole point is just, I mean, this example, the specifics are not important. The example is just that this language may be primitive and simple, but that is not only, I mean, not just a disadvantage. It has the advantage that it's so simple that I can write something like this, which takes such an expression and analyzes it for problems. And it, of course, doesn't necessarily have to be problems. I could do all sorts of things. I mean, I could write a compiler, for example, for this language, or I could other analysis tools. Maybe a tool that tells me how many execution steps an expression will need to evaluate, or things like that. So the point is, this DSL is so simple that it allows me to provide strong tools for static analysis. So static means tools that I can use to analyze a program without needing to execute the program. And on the other hand, like some programming languages, like for example Haskell programs, because or related to the fact that Haskell is Turing complete, are make it impossible to write general such tools. I mean, you can still have tools that can maybe analyze a certain class of Haskell programs, but you can't. It's not as powerful because the language is so powerful that it's basically impossible to write very powerful static inspection tools. And for Marlowe, we want powerful static inspection tools because potentially a lot of money is at stake. So the idea of Marlowe is to make it both simple and secure. And one of the consequences of that desire was to make it non-Turing complete. And that then, I mean, of course, not every I mean, the fact that Turing complete implies halting problem doesn't have a solution doesn't mean that non-Turing complete languages automatically are analyzable. I mean, that's would be like logically wrong to conclude that. But I mean, if it's Turing complete, you don't even have a chance. So Marlowe, by not being Turing complete, does have a chance, and it has been carefully designed in a way that indeed makes it possible to do static analysis. Right, and Marlowe is not completely unsimilar to this. I mean, it's obviously a bit more complicated, but also not dramatically more complicated than this type. So I would suggest we have a short break, maybe 10 minutes, and then after the break, we'll actually look at Marlowe and then write some example programs in it.
Okay.
So are there no
Yes.
questions at this point? Then we can have a short break.
Yeah, I think so far there are no questions.
Okay.
Yeah.
Okay, good. Then let's talk in 10 minutes.
Okay.
Okay. Questions so far?
I think no questions.
Okay, good. Right. So now let's talk about smart contracts. But before we talk about smart contract, let's talk about, I mean, just formalizing contracts, not necessarily, sorry. Right. Right. So, I mean, normally when we talk about contracts, I mean, if I say contract, then probably most of us think of like a written document in English, for example. Of course, can also be Swahili or whatever. And of course, it's normally contracts are written in a very like formal English or formal language. I mean, some jokingly call it legalese, which tries to make the terms of the contract as clear as possible and unambiguous. But nevertheless, that's never achieved in normal contracts. There's always dispute where the parties to the contract interpret it differently. And with normal contracts, in order to solve these disputes, there are various legal instruments, like you can sue the other party or take a lawyer and go to court. And then a judge or a jury or whatever decides on the interpretation of the contract. So the idea of formalizing that is to replace all this ambiguity, which is caused by like natural language. I mean, the fact that English sentence is never 100% clear, what the meaning is never 100% clear, to replace that with some formal language that is completely unambiguous. So the idea is then that you basically don't have this problem anymore, that parties don't fully understand what exactly the contract says. And incidentally, there's this paper from the year 2000 where one of the co-authors is Simon Peyton-Jones, who is also one of the original creators of Haskell. So as I said right in the beginning, Haskell is designed by committee, and Simon Peyton-Jones was one of the members of that committee. And he, I mean, if there's one person that you would say is like most influential for Haskell, then it would be him. So he's like one of the main authors of GHC, the compiler we are using. And to this day, I mean, he's very engaged in like extending Haskell and maintaining it and developing it further. So anyway, in the year 2000, he took on this task of trying to formalize financial contracts. And that was, of course, 8 years before Bitcoin. So nobody was talking about blockchain then. So this was about normal financial contracts. So the idea was to somehow turn the English ambiguous language of contracts, of financial contracts, into a DSL written in Haskell that would make the meaning of contracts very clear. And I mean, it's a beautiful paper. So if you feel like it, you find it online, composing contracts. And the details are not important for us, but this is basically it. So it's a domain-specific language which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 constructs. So 10 primitives, 10 building blocks, and those allow you to model an amazing variety of real-world financial contracts. So one of the features is that it's composable. So for example, you have this then here, which takes 2 contracts and composes them into a more complex contract, or this or and. So basically that's the idea, that you have like a few primitives. So the simplest one is this 0 contract that doesn't do anything. So 0 basically means the parties to the contract have no obligation. No money is paid, nobody has to do anything. And then there's this one where one party of the contract has to immediately pay 1 unit of currency. And then with these very extremely simple building blocks, and then some combinators like then and or, you can build an amazing variety of real world financial contracts. So the cool thing about this is that very few primitives and then combinators that allow you to assemble simple contracts into more complex contracts were sufficient to model a lot of real world contracts. And that's of course similar to, for example, the idea of IO monad or monads in general, where you have very few primitives, like in the state monad, just get and set. And then because it's a monad, the bind, you can like assemble simple primitive computations, in that case, to more complex ones. And it's a similar idea in this paper here, to have very few primitives and combinators to combine simple contracts into more complex contracts. And that was a very influential paper. And it was also the inspiration for Marlowe. So Marlowe, when like the team started designing Marlowe, they took their inspiration from this paper. I should say, it's not all, like everything in life, it has advantages and disadvantages. So of course it sounds like a disadvantage that traditional contracts can be ambiguous and the meaning is not completely clear. But on the other hand, it can also have an advantage if there's a human in the loop. And for example, in the case of traditional contracts, courts, consisting of human judges, can decide. Of course, that means that if for some formal reason, or if there's something that's clearly against the spirit of the contract, some sort of loophole, then a judge can still basically declare that this is, even though it may be technically correct, it's clearly unethical or whatever. And of course, if you formalize something, then even if you're not happy with what the contract says, there's no way to escape that. So an famous example in blockchain happened with Ethereum some years ago, the famous DAO hack. So Ethereum was the first blockchain that introduced so-called smart contracts. So the idea of a smart contract is to take something like this paper, and apply it to the blockchain world. So to have something so that, the like first generation blockchains like Bitcoin, first generation cryptocurrencies were very limited. They, in principle, you could only send money from A to B, which was already like revolutionary for the time. It's possible to build something like decentralized money without a central backing authority like a central bank, and without the need of trust, where people don't necessarily have to trust each other and can still rely on the fact that the blockchain is safe. But in principle, it was limited to people sending funds from A to B. And then Ethereum what we call blockchain of the second generation introduced smart contracts. So the idea was that it's not just these people that can send money, but that there are contracts. So intelligent rules that determine under like more or less arbitrary conditions, under which conditions certain payments can be made or have to be made. And so Ethereum was the first blockchain that had smart contracts. And there was this DAO, decentralized autonomous organization. So people use smart contracts to basically build companies on the blockchain, where it's not a traditional company that has is registered at a specific geographic place in a specific jurisdiction. But the idea was basically the treasury of the company is governed by a smart contract, and then people can vote, for example, on what that money is used for. So if somebody wants to take part of the treasury to whatever, pay some development, then there could be a vote, and then if people voted on the blockchain, then those funds would be released. And there was a famous bug in Ethereum, or in the not really a bug. It was more because the Ethereum smart contract language was so incomplete and relatively complicated. There was a loophole. So somebody figured out that you could steal money from this DAO contract, so basically drain the treasury. And of course, I mean, whether that's like an interesting ethical question, whether that's even theft. I mean, one standpoint, I mean, there are 2 points of view you can take, right? I mean, one is that clearly the way this contract was defined, I mean, there was a certain intention behind this DAO that people can vote and so on. And if somebody finds this loophole and drains the treasury of money, that's clearly unethical and theft. But on the other hand, after what I said before, you can also say that the whole point of smart contracts is that you don't need interpretation anymore. You don't have to worry about intent and spirit anymore. You can just follow the rules. The rules are basically mathematics, clearly written in a formalized language, in a DSL, in a programming language, and the contract is exactly what it says it is. And if there is some loophole, I mean, it's just one of those things. I mean, it's there, and if whether people intended it to be there or not, I mean, it's part of the contract, so there's nothing wrong with exploiting it. So in any case, somebody figured it out, stole a lot of money. I think it was almost $100 million worth of Ether. And then this ethical or moral debate started in the Ethereum community, what to do about it. I mean, some factions said, well, it's just how smart contracts work. So it's just one of those things. So we must just be more careful writing them. So the person that took the money should get away with it. And the other faction inside the Ethereum community argued that that was clearly not intended and was clearly wrong, and one should basically revert it. So all the Ethereum nodes should agree to basically stop operation of the blockchain and unwind the last, 48 hours, and basically reset the blockchain until before this event happened. And the debate basically could be resolved. So like a relatively large chunk of the Ethereum community was of the one opinion and the other part of the other opinion, which led to a so-called hard fork, where one blockchain splits into 2 blockchains. So there was one part that reverted it. So they basically dropped the last 2 days of transactions and went back to the state before this event, and basically made it so that it never happened. But by that also violated the spirit of smart contracts, that they didn't just follow the rules, but basically decided that this was intentional, so let's revert it. And then another part of, so it split, that was the one part, and the other part, people that said, okay, fine, we just let it be and let the person get away with taking that money. The bigger faction was the former one that reverted it. So that's what we call Ethereum today. But there's these days also Ethereum Classic, and that's the other faction that decided to not revert this event. Right. So my point is just that, I mean, it's not always, it's not all good or all bad. I mean, there are advantages to having humans make moral calls or ethical judgments. Nevertheless, I mean, this DAO event also showed that one problem with Ethereum was and also is that I mean, nobody saw that coming. So the contract was so, I mean, the whole programming language that Ethereum uses was obviously so complex that people overlooked this loophole. So one of the design choices of Cardano for Plutus, but also for Plutus, but also in particular for Marlowe was to make the language so simple that you can easily see or even mathematically prove that things like that are not possible, that nobody can steal your money basically out of the contract. So right, so Cardano tries to improve on Ethereum in that sense, so that smart contracts are easier to analyze, easier to understand, and that it's less likely that something goes wrong. And as I said, that's true for Plutus, so we will talk about Plutus next week. And it's certainly more secure, I think, much more secure than Ethereum is. But nevertheless, Plutus is a Turing-complete language. So like theoretically, it's impossible to know for every Plutus contract what exactly can happen. But Marlowe is much simpler, as we will see just now in 2 minutes. And in Marlowe, there are lots of static analysis tools that make it possible to give very strong static guarantees. So before you actually run the contract, you can analyze it and have a very good idea of what can and cannot happen in a Marlowe contract. And as I said before, today, I don't really want to look at Cardano, so I don't want to demonstrate Marlowe contracts on Cardano itself. I can do that in the next lecture. So today, I just want to talk about the language. So as I said, it's heavily inspired by this paper here. But oh yeah, one other thing I should still say. Maybe I can go back to the editor. So I mean, we have this paper, this Simon Peyton John's paper, but differences between blockchain and real world contracts. So, I mean, something like this, I mean, one could ask, why don't we just use that? If it was such an influential paper, why don't we use this DSL, this domain-specific language for financial contracts, to implement Marlowe, to do it on the blockchain? And if we, for example, look at this contract 1, it's a contract that immediately pays the holder 1 unit of the currency K. The contract has an infinite horizon. Let's not worry about the horizon part, but just this first sentence. It's a contract that immediately pays the holder 1 unit of the currency. So for a real world contract like these are, it's fine. I mean, you have this contract, Karina and I sign a contract, and so I am obliged to pay her whatever, €1. So what now? I mean, what if I don't pay? Then Karina can sue me at court. I mean, obviously, in a case of €1, probably that wouldn't be very successful. But if it was €100,000, then probably, I mean, she could definitely go to court. And then if I'm found guilty, I mean, the court could, whatever, confiscate my assets or even threaten to throw me in jail. So there are ways to enforce a contract in the real world using the judicial system, using the police, and so on. On the blockchain, that's not the case. I mean, on the blockchain, I mean, we haven't talked much about blockchain yet, except on the very first day, and we'll talk more about that on Thursday and also when we talk about Plutus. But I mean, we already can say that, I mean, a blockchain consists of transactions that people do, and nobody can force you to make a transaction. And I should also say that blockchain is only transactions. So the only thing that's on a blockchain, or at least on a cryptocurrency, is these financial transactions. And those transactions are always triggered and signed by somebody. I mean, normally human beings. In principle, of course, you could also write some software program, some agent that could issue transactions, but nevertheless, it's always external events. So the blockchain is a passive thing. It's like a I mean, it's really like a database. I mean, in the beginning, at some point, I said it's like a write-only database, and it's really like that. So databases don't just do stuff. I mean, they passively wait for data to be fed to them. And the same is true for blockchain. So, for example, you can nobody can force anybody to do anything, like make a payment. Blockchain doesn't do anything. Every change is triggered by an external event, transaction. Right, so for anything to happen on a blockchain, there must be a trigger, and these triggers always have external causes. So it's always some agent, some human being that makes a transaction. Without people like actively sending money or making transactions, nothing happens on the blockchain. I mean, if the nodes are working, there will still be blocks, but they will be empty. And basically the state of the blockchain, the who owns how much, won't change. So there's no way, I mean, it's like, I mean, with traditional finance, even, I mean, if I don't want to pay Carina, then some judge can order the bank to, I mean, the bank can freeze my assets, for example. Or somebody could just take my money and, like the police, or could take my money and send it to Carina. But on the blockchain, that's not possible. So, I mean, there's nothing that can make me make a payment, for example. And therefore, smart contracts on a blockchain have to somehow work differently, like substantially differently to how contracts in the real world work. Because they're in some sense much more passive. They basically can react to events, but they can't do anything by themselves. There's no action. They can't force any participant to do anything. That's also the reason why contracts often work differently. I mean, for example, one of my favorite examples for smart contracts is auctions. So if you have a real world auction, then like at Sotheby's, you auction for some work of art, like a painting, and people just sit there and make bids. And then in the end, I mean, somebody has the highest bid, and then basically that's a legal contract. I mean, he gets the painting, but he also has to pay. And if he doesn't, I mean, if he just made the bid without any intention of ever paying, then he would be in a lot of legal trouble. So basically the auction house can make him pay. And on a blockchain, if you want to do an auction on a blockchain, I mean, you could try to do it the same way, but then if somebody wins, there would be no way to force him to actually pay the highest bid that he made. So that's why on the blockchain, people normally do it differently, that in the beginning, everybody that wants to participate in an auction has to make a deposit, for example. And only if you have made that deposit, you can participate in the bidding. And then in the end, everybody that lost gets their deposit back. But the highest bidder, I mean, he has already paid, so the auction house can just keep the deposit. So it's this, like, it requires you to think differently. So, I mean, things are still doable, like auction, for example. You just need an often you need different methods to achieve the same goal. So where in like the real world for auctions, you can rely on people being forced to honor their commitments. If they said they would pay so and so much for this painting, then you can force them to actually do it. On a blockchain, you need some other ways, like making everybody pay in advance and then just reimbursing people later. And if you don't pay in the first place, you can't even participate. Right, so that's reasons like that you can't just take the Simon Peyton Jones paper and take it one-to-one on the blockchain. You have to modify the constructs. And so now it's time to actually look at the code. And unfortunately, it might be a bit outdated. I don't know what version is actually right now active. I think this is the newest version. I just looked that up on GitHub. And right, so this is the central Marlowe type for Marlowe smart contracts. And as you see, as I promised, it's really not much more complicated than this expression type that I showed you earlier. I mean, I'm cheating a bit because this type mentions other types like value, for example, which are also defined here. But I mean, even so, basically from here to, I think in principle, this here, these two screens or so, that's Marlowe. So it is very simple. And even this contract type here, like this one, for example, is actually not really necessary. So it only has like very few constructs. And I think we just now play around a bit with these contracts and get a feel for it. So we don't have to look at every single like thing here. I think it's more important to get a feeling for that. Okay, and so as we see here, Marlowe is just like my expression type. It's a Haskell data type. So one way to write Marlowe contracts is in Haskell, like constructing a value of this type, same as I constructed my example program in the example I gave earlier. But I think but luckily there are other ways. And I think particularly for beginners like you, the nicest way is a different one. So not writing it in Haskell. And Marlowe provides the so-called playground. Which is at play.marlowe.iohk.io. So that's the Marlowe playground where you can create Marlowe smart contracts and also play with them in a so-called simulator. And then on Thursday, we will see how you can, instead of just playing with them in the simulator, also deploy them on the real Cardano blockchain. But today, let's concentrate on this playground. The playground has various modes. So if we go to a new project, we see we can use Haskell. So it has a Haskell editor integrated into the browser. So you can directly in the browser use Haskell to write a Marlowe contract. It also, to my despair, contains a JavaScript editor. So you can also do it in JavaScript instead of Haskell. Marlowe is basically just the value, the Haskell value of this type. So I think it's impractical to do that directly. And lastly, there's this Blockly. And Blockly is a graphical language. So you don't have to write a single line of code. You can basically just drag and click Marlowe contracts together. So that's how I want to start. And then, like in the last part of today's lecture, switch to Haskell and do some a bit more complex things there. But let's first use this Blockly. So the idea is that basically you can't do anything wrong. Everything that I mean, there are these puzzle pieces and you have these various constructs. So here's what we saw earlier in the Haskell code for Marlowe contract, now in form of these puzzle pieces. And they always have like certain slots where you have to fit in other puzzle pieces, and only like puzzle pieces of the right type fit into the slot. So if you can make everything fit together, then you have a valid Marlowe contract. And the top level, I mean, what we want is a contract. So there are different types as we see here. But I mean, what we top level want is a contract, as I also said. Sure, no, sorry. So that was, yeah, let me just move this bar quickly. Sorry. Yeah. So what I showed you here in this Marlowe Cardano repository, so this is the main type. This is the type of Marlowe contracts. So we want to construct a value of this type. And now we will do it with Blockly. So in the end, we will have a value of this data type. Although I'm not 100% sure that this newest version here of the Marlowe Cardano corresponds to the version that the playground uses. But I think if there are differences, they are hopefully not significant. Right, and when you start a new project, then this is what you get initially. And this is also the simplest possible contract. And that's also, if you recall, in the Simon Peyton Jones paper, there was this zero contract that doesn't do anything. So the equivalent of that in Marlowe is this close contract. So that doesn't do anything and immediately stops. Now we can, here these buttons, view as Marlowe and send to simulator. So if you view as Marlowe, then we basically see the Haskell value corresponding to the contract. So in that case, it's just the close constructor. So if we go back to the code, you see here the first constructor is close, so it's just close. I mean, it's very boring. And if I send it to the simulator, then I can say when it should start. So I think this is now, and I can do start simulation. And it's very boring because it says, I mean, it's done. No valid inputs can be added to the transaction, which means it's done. It's closed. And nothing happened. I mean, contract started 1546, contract ended 1546, and nothing happened. But nevertheless, it's a very valid contract. Let's go back to view as blocks, and let's do something more interesting. So let's see what other, instead of close, what else can we do? And there is this when, so we'll come to that in a second. Pay and if. Let is basically just let in Haskell, so it's variable. So, I mean, this is not even strictly speaking necessary, I think, just for convenience. The third is also more for debugging, so it's not really, so I mean, those three are like the main ones. And of course, it seems, or we would think that pay is like easy. I mean, let's say I want to, one person, Alice, wants to pay 100 ADA to Bob or something. Sorry. The problem is though, if I recall what I just said, that on a blockchain you can't make anybody pay anything. So this pay is not what you think it is. So let me just go back to where I can write something. This is like Marlowe accounts. As you will see in particular on Monday when we talk about Plutus, when we briefly talk about accounting models, I mean, you are used to like bank accounts where like you have a certain balance on your account, and if you transfer money to somebody else, then that money gets subtracted from your balance and added to that other person's balance. That's not how Cardano works, and it's also not how Bitcoin works. Bitcoin and Cardano use the so-called UTXO model, which works differently. But that's not important for today's lecture. Because Marlowe actually also uses something similar to these accounts that you are used to from banks. However, Marlowe has this has basically like external parties, and internal accounts. So Marlowe has this concept of parties to a contract. So it can be two people. I mean, it can even just be one person. You could have two or more, but it's always a fixed number. So it's always like a known in advance number of parties that participate in a contract. And as I explained before, you can't force anybody to do anything on the blockchain. So you can't force any party to make a payment. But in order to make things a bit simpler, Marlowe has this contract of internal accounts. So for each external party, there is an internal account in a Marlowe contract. I mean, that's just a virtual thing that doesn't really exist. It's just like conceptually. So each external party has an internal account. So automatically, when you create a Marlowe contract with certain parties, then associated with every external party is an internal account. And that is something the contract does have control over. So I said earlier, you can't force anybody to do anything, but once money is in one of these internal accounts, then the contract actually can make payments. So to go back to Blockly, this pay actually always the originator, the source of the funds of the payment is always an internal account, because Marlowe can only has control over the internal accounts, because you can't force an external entity or person to do anything. So we can't use this pay, because at the moment in the beginning there's nothing, no money in the internal accounts. You can't. I mean, Marlowe's contracts start with balance zero. So maybe I should add that. Initially, all internal accounts are empty. And maybe while we are at it, I should just, I mean, we had this close contract and I was a bit derisive and said it doesn't do anything. But actually, there's one thing it does do apart from stopping the contract, and that is it cleans out the internal accounts. So upon close, if there's any money left in any internal account, when you close the contract, it gets paid automatically to the external parties corresponding to that account. So maybe I should write that here. On close, all funds in internal accounts get paid to the corresponding external party. Right, and I think this is now enough preliminaries to, right. So in order to do anything, I mean, for example, if Alice wants to, using Marlowe, which you wouldn't, I mean, if you just want to make a payment, you do it in the smart contract. But if we want to do something like this, then we first need somehow a way to get money into one of these internal accounts. And that's what this when is for. So we need this. And we can slot the when in there. So when waits for an external trigger. So a when contract doesn't do anything by itself. It just waits for something to happen. And then, so what happens and what it does, if it happens, goes in this first slot. And then there's also something, all Marlowe contracts always have a finite lifetime. So there's always, you can always say how long it will run at the most. Now, if you think about it for when, if you wait for an external trigger, because it's an external trigger, you of course don't know when somebody will trigger this external trigger. So in that case, you wouldn't be able to say, okay, the contract will run for at most a day. That's why Marlowe has this concept of timeout. So in this case of when, of external triggers, you always have to give a timeout. And that means if none of the external triggers defined here happens until that timeout, then the contract will stop waiting for anything to happen and will instead continue with whatever you write here. So for example, okay, and now, so we have to say what it should wait for. We should say what should happen after the timeout. and we should say what the timeout is. And as you can see here, I could just specify it. I mean, I can do that now. Whatever, I can put a time there. This is now from, it's maybe, okay, fine. Let's make it a little bit later. But it's fine. I think I can also configure the start time. I mean, for example, one thing I could do is leave this here empty and just say continue as close. So this is now almost as boring as my first example, but maybe not. Here, see, I could also, I mean, now it starts at now, I mean, the real now, but I could also put a different start time in here. So the times don't really matter for the simulator. So if I now say start simulation, it's not immediately done because now I have these options here. I can, for example, advance time. Oh yeah, and on the left, we always see the active Marlowe contract. So the part that's just being simulated. So this is the whole contract. And we see that this time 1604 4 p.m. and 5 minutes got converted into this long number. So that's somehow POSIX seconds. So it's a Unix timestamp. Doesn't really matter. But we see, so this is like the Haskell when it's waiting for these conditions, but it's just the empty list. I didn't define any conditions. This is the timeout, and this is what happens once the timeout has been reached. So now in the simulator, I can, like, for example, advance time by 1 minute. If I do that, I mean, only this here changes the current time, but nothing else happens. Then I can also go to the next timeout, which in this case would be this, so 1605. So if I do that, then the contract ends and nothing has happened. So I mean, all this does is, again, nothing basically, but at least in the simulator, I can do like stuff. Okay, but now to make it more interesting, what can we write here? What are the external things we can wait for? And that is called an action. And we see, I never understood, and to this day don't know what notification is good for, but those two are interesting. So let's start with deposit. So this is, so deposit means, so this when is waiting for an external event. And this deposit means the external event is that one of the parties to the contract makes a deposit, which means he, like, externally from his own money pays to one of the internal accounts. So now you have to fill in, like, who makes the deposit, how high is the deposit, what currency is the deposit, into which internal account does it go, and what should happen once this happens. So I mean, I said when waits for an external trigger. So this is the trigger, and this is the action it should trigger. So for example, we can acquire this buy. This is a party, I think. Or is it yeah, it's a party. So there are now again two ways how to identify these parties. One is by an address on the blockchain. So we will talk about addresses more on Thursday, and also when we talk about Plutus. So basically, like, that's like an identifier on the blockchain, like a account number on a bank. So I could put some, but those are normally like quite long hexadecimal byte strings. That's for the simulator, it's a bit unwieldy. Alternatively, there's also this role thing, and this is much nicer for the simulator because I can freely choose a arbitrary string here, for example, Alice. And if you actually run that for real, as we will probably see on Thursday, this is done with a so-called NFT. So I don't want to go into too much details, but NFTs, non-fungible tokens, are like coins, tokens on the blockchain that only exist once. And they can be used for all sorts of things. So people use them for artwork, for example. But for Marlowe, they are used to identify roles. So if I would actually run this thing on the actual blockchain, then associated with this role would be an NFT that identifies the person incorporating this role. So whoever has the NFT is allowed to participate in this contract in this role, which is actually quite nice because it also means, I mean, NFTs can be sold or given away. So this is a mechanism where you could basically have like different physical people incorporate the same role in a Marlowe smart contract by passing on this NFT. But nevertheless, so let's not worry about that now. For the simulator, we can just think this is just a party to the contract and it's called Alice. So I can put that here. So now how much? Let's say, so this is a value. Values we have here. So there are various constructs. The easiest one is a constant value. But we can also do arithmetic on values. We can add them, subtract, multiply, divide. This goes into choices, so we'll come to that later. This is not so important, I think. And this is if we use variables, and we can even define them conditionally depending on some Boolean. But let's just say 100 ADA. So let's use a constant value. Probably not sure. I probably have to use loveless. So that means if I want 100 ADA, must be 100 million loveless. Now the currency that's, sorry, token. It's called token here. So Cardano has custom tokens. So everybody, including you, can create your own tokens if you want. And those things are identified by two pieces of data, so-called currency symbol and a token name. But like the main currency on Cardano is called ADA. So let's just go for ADA. Oh. Right. So this means, so wait as an external trigger for a deposit made by Alice of 100 ADA. Now I must say where. So it must always be an internal account, but it doesn't have to be her own. She can also pay into somebody else's account. For example, Bob. Let's say Bob. So let's into account of. So that's again party role. Let's say Bob. Okay, and once this happens, now I can say what should happen next. And I can again be boring and say nothing happens next. But now this is a contract that where finally something will happen. So hopefully, so let's see. So if I now start this, so here you see again this whole thing now in basically in Haskell, like displayed as a Haskell value. So start the simulation, and I again could like step time forward, for example. So for example, if I step until 16:05, then I'm done again because the timeout has been reached and it closes without anything happening. But I can also, like, now I have this additional option here. So as I said, so the when clause contract is waiting for something to happen, one of these cases in this list. In this case, there's only one. I'm only waiting for this deposit. And now this simulator allows me to basically simulate these external events. So I can now, this now says participant Alice could can make a deposit of 100 ADA from her wallet into Bob's internal account. So I can decide to do that now. Now the contract is again done because we set up, we also see this has been highlighted here. So the highlighted part is always the active part of the contract. If I go back again, we see everything is highlighted. So we are basically at the state where this is the active contract. But as soon as this trigger happens, so Alice makes the payment this year. So the contract has reduced to this part because the trigger has happened. So now we are in the continuation here. And the continuation is just a boring close. But now, because of what I said earlier and what I also wrote down here, on close, all funds in internal accounts get paid to the corresponding external parties. And because Alice made a payment to Bob's internal account, upon close, the contract pays Bob's internal account to his external wallet. So that means that in effect, what this now did was that Alice was sending 100 ADA to Bob. And we can see here these events. Contract started, then 2 minutes later, Alice deposited 100 ADA from her wallet into Bob's account. And then, because we hit the close, the contract pays 100 ADA from Bob's account to Bob's wallet. So in the end, Alice paid 100 ADA to Bob, basically. Now, one small thing, I mean, before we get to more interesting contracts, one slightly annoying thing is that I had to hard code this 100 ADA. I mean, maybe we want to do it with 1,000 ADA or with 500 ADA. So Marlowe has you covered there, and that is the so-called extended Marlowe. So like basic Marlowe only has only these constant values. And extended Marlowe is slightly extended by allowing so-called templates. So for certain values that normally you would need to hard code, extended Marlowe allows you to basically make it configurable with a parameter. And one of those positions you can do that is for values. So if I remove this constant 100 million and look what is available for values again, I see this param, constant param. So I can instead use that and give it a name, for example, amount. And something similar is also possible for timeouts. So instead of using a constant timeout, I can use a parameterized timeout and I can give it a name. For example, payment deadline. Okay, and with these changes, if I now send it to the simulator, I have these two additional fields. So I again must say when it starts, but now for this time parameter, I can specify it here in the simulator. So it automatically shows a time 5 minutes after now, but I could now edit that and put tomorrow or in 10 years or whatever in there. And the amount. So this amount I must now enter here. So for example, I can do 200 ADA. If I now start the simulation, we see now it's depositing 200 ADA. So to be clear, when the contract is actually executed, all the parameters have to be filled in. So the way it works is, as we will also see on Thursday, when you have such a contract that uses parameters, it's then a so-called template for contract. And before you deploy it on the blockchain, you have to pick values for all these parameters. And then you pick the values and then you deploy it. So now, of course, the same again, if I make this payment, then in effect, now 200 ADA go from Alice to Bob. And maybe one last thing. I'm not sure whether it's the last thing. We see static analysis here. I'm not sure whether this is interesting enough. But this is what I spent the first hour basically explaining, that because Marlowe is so simple, in particular, it's not Turing complete. It allows like strong static analysis without having to execute the contract. And this is basically just a proof of concept here. So there can be many more things you could potentially do, but the creators of Marlowe have implemented some of these static tools into the playground. So just to show what's possible. And so these three are, I think this checks whether could be any warning. And I expect there's, okay, cool. This is a bit weird, but because it somehow assumes that, sorry, it's not weird. I'm okay. Also, the static things only work once you have specified values for the parameters. So I didn't do this now. So it's still, the amount is still set to 0, and then I get the warning that a non-positive deposit is made. So of 0 ADA, which is true. And what's also cool is it basically tells me when that happens and what sequence of events leads to this warning condition. So in this case, it's very boring because not much is happening here. So the sequence of events is just transaction starts and then the deposit happens. But if we had a more complex contract, then this would tell us exactly what needs to happen in the contract, who has to do what in order to get to this warning condition. So let me fix that by putting 200 there again. And maybe make this 15 or something. Right. If I now analyze for warnings, I think I won't get any. Now this reachability checks whether there are any parts of the contracts that can never be reached. There are none in this case. And this analysis for refunds, it says when first case. So when first case is this deposit, close. So it tells me that a close happens. And as I explained before, implicit payments are made on close because all the internal accounts are emptied. So this is what this analysis looks for. I did that intentionally because I wanted to use this mechanism to get funds from Alice to Bob. But I mean, of course, that may be something that the contract author doesn't expect. So therefore, there's this warning here. If I want to get rid of that, I can replace the close with a pay. Now I can actually do a payment because now there is money in an internal account. Okay, so payee is who gets paid. So instead of letting the close take care of this, I can make that explicit, this payment. So I can explicitly pay Bob. So the payee is Bob, and payee can be another internal account, or it can be a party. In this case, I want a party, namely Bob. The amount of, well, the same amount, so this one. There's also, I think, available currency from account. So I could also use this instead, just for variety, which says all the money that's in a specific internal account. So available ADA from account of Bob. Of currency ADA from account of Bob. So this is exactly the payment that would have happened by the close implicitly. I make that as an explicit payment now. And then afterwards I can close. So this should behave exactly the same as before. So if I send it to a simulator, let's add a couple of minutes here. Start the simulation, it should be exactly as before. So if I make the payment, then in the end, Bob ends up with it. The only difference is now if I go back to here and do the analyze for refunds and close, then nothing is found anymore. So it detects that when the close is reached, all the internal accounts are empty at that point because I made the explicit payment before. So I cleaned out the internal account before it comes to this close. And this close, at that point, there has been no deposit yet, so everything is empty. And the point is just, I mean, I don't know how useful these two things are, but the point is just that it's possible to write these things. So you can write your own analysis tools, or people can write, I mean, third parties can write, or IOG can write these analysis tools that look at the Marlowe contract and analyze it and then check certain conditions. So for example, in this case, that on close, no money is left in any of the internal accounts. And also, if we, as we saw in the send to simulator, sorry, if I do this, then here we see the expiration time. So it automatically realizes that the contract will be done 1620. So that's also a static analysis. It checks the deadlines in here and sees basically if the deposit happens, it stops immediately, but there's this deadline, so it can figure out that the contract will, under all circumstances, be done by that time. So that's also something, I mean, as I saw, with the halting, or as I explained with the halting program, I mean, with like Turing complete languages, you don't even know whether they will ever stop, let alone when. But with a Marlowe contract, it's always possible to say, to give an explicit, specific time when it will be done. That's also an example of static analysis. So I think we should have another 10-minute break. And then after the break, look at some more interesting contracts, use some of the other constructs. I mean, right now it's all very boring and nothing that you couldn't do without smart contracts. So let's do that after the break, except if there are any questions now.
No, I think so far there are no questions.
Okay, then if you have any, you can of course also ask them later after the break. So let's have 10 minutes break again. Was there something?
Yes.
Okay.
Okay.
Okay. Bye. See you soon.
Question, Lars.
Okay. What
So,
question?
Can ask on simulation or deployment, at what point does translation happen from accounts to UTXO?
I mean, the accounts are just virtual, so there is like a data structure that keeps track of that. So, I mean, the external wallets are just UTXO, and then if you make a deposit into the contract, it's also a UTXO, but the contract just has a certain amount of money in one UTXO, and then it somehow has a data structure. So we will talk about data in smart contracts on Monday. We talk about Plutus, so it will somehow keep track of in which account is how much, but it's only virtual. So everything, all the money that's deposited in the smart contract is basically in one UTXO concentrated. But then there is a piece of data that knows that so and so much belongs to Alice, so and so much belongs to Bob, and so on. So to basically give the illusion for people that, I mean, to make it easy to think about it, because I mean, one of the intentions of Marlowe, design of Marlowe, was to, I mean, make it easy for non-programmers, for finance people, for financial experts to work with Marlowe, because those people normally tend to think in accounts and not in UTXO. I mean, that was one of the reasons, I think, why they designed it that way, to make it easier for people to work with it. But under the hood, it just works with UTXOs, and somehow some data keeps track of how much is in those virtual accounts. So it happens at the moment of deposit, basically. So when somebody makes a deposit from an external wallet into this smart contract, this Marlowe contract, then at that point, basically it's treated like sitting in a virtual account. I hope that answers the question.
Yes, thanks, Say.
Okay. Right, so let's now try to do something a bit more interesting, where it's not just these deterministic payments, but where there's some choice point. And there's something, concept called choices in Marlowe. So let's do something very simple, where Alice and Bob make deposits, and then Charlie can pick one of the two, Alice or Bob, and whoever Charlie picks gets both the deposits. I mean, it's not a very realistic example, but just to show what's possible. So back to edit source. Let me remove this payment here. Right. So at this point, Alice has made a deposit into Bob's account. Let's just change that to Charlie. Right. So now let's also let us make, Bob make a deposit as well, same amount. So once Alice has made her deposit into Charlie's internal account, we wait for Bob to also make a deposit into Charlie's internal account. So I just copy this whole when thing and paste it again and slot it in here. And now change this to Bob. And of course, lots of things can go wrong. I mean, for example, Alice can never make a deposit, in which case this timeout will be hit and nothing happens. Or Alice makes her deposit. Right. Sorry. Yeah, exactly. Sorry, was thinking. So now if Alice makes her deposit, but Bob doesn't, then this timeout is hit. And this is not really, so if on that close, because Alice made her deposit into Charlie's account, now Charlie would get the money, which is probably not what we want. So it's probably better if we have people pay into their own internal accounts in the beginning. So now, I mean, we can actually simulate it. I can just put a close as well. I mean, this is not the final thing that I want, but let's just see what can happen until now. This deadline is now 50 or something. Doesn't matter. 50. Right. So now it starts as before. Alice can make a deposit. So if Alice doesn't make a deposit until the timeout is hit, then nobody has paid any money. So that's really boring. So if Alice makes a deposit, so now we have Alice deposited 200 ADA from her wallet into Alice's account. So now Bob can fail to make a deposit. In which case now, because Alice paid into her own account, when the contract is closed, she gets her money back. But again, boring. So the interesting case is that both make the deposit. So, but now, of course, because of this clause here, again, both get their money back. But now we can continue. Let's now say that instead of this clause, now we want Charlie to make a choice. So that's again a when, as before, but now we use a different trigger. Why is that not working? No. Right. And let's use a different timeout for him to make his choice. So let's call it a decision or choice deadline. So if he doesn't make a choice, we just close as before. Right. So now we want to, instead of waiting for another deposit, we want to wait for a choice. So that's these actions here. So we had used the deposit until now. Now we can use this choice trigger. So choices have a name. In this case, because there's only one choice, doesn't really matter. Let's call it winner. We think of this as a lottery or a game or something. Choice owner is the person that is supposed to make the choice. So we said Charlie. So I just plug Charlie in there. Now choice bounds. Choice always has finitely many values, integral values with a lower and upper bound. So in this case, 1 and 2 is fine because we have two people, Alice and Bob. So we can just say Alice is 1, Bob is 2. So Charlie must choose one of the two. So we plug choice bounds in there, but we could edit these fields. So it can be like more choices than just 2, 1 and 2. Okay. So now after this choice has been made, we continue. And now what do we want to do? We want to, if Charlie picked 1, which is supposed to mean Alice, then Bob's money is supposed to go to Alice. And if he picks 2, then Alice's money is supposed to go to Bob. So now we need what we also haven't used yet. So we have used I showed you the pay. So now there's also the if. So there we have so-called observations, which are basically Booleans. Now we want to make what happens next dependent on the choice. So if we look at observations, we see there are Boolean combinators and or not. And then there are things involving values. So we can check whether value is greater or equal or less than equal. And we also have true and false. And we have this one, which involves choices. Okay, but this is only right. But this is not the one I want, because this only tells us whether a choice was made or not. But we know that choice has been made at this point, so this is not interesting. What we want to check is the value of the choice. We see here at values, somewhere here. This is the value of a choice. So we want to check whether that is 1 or 2. So with observations, we can use this value is equal. And so as value, we take the value of a choice. So we named our choice winner. And it was made by Charlie. So this value here is now 1 or 2, depending on what of the two Charlie chose. So now we can check whether it's, for example, equal to 1. So just use constant 1. So this observation is now true if Charlie picked 1, and it's false if Charlie picked 2. And if it's true, then this contract will be executed. If it's false, that contract will be executed. So in the first case, we want the money, all the money go to Alice. Recall at this point, Alice has 200, or the amount in her internal account. Bob has the amount in his internal account. So there are several ways we can do this. I mean, for example, we can make a payment from Bob's internal account to Alice's wallet, but we could also just transfer it to her internal account and then let the close take care of the rest. So maybe just for variety, let's do that. So we make a payment. Okay, payee is who gets paid. Let's now say, I mean, as I said, doesn't matter in this case, but we can say account of Alice. Did I do now? That is. The amount of, again, we can say constant amount, for example. We could also use everything that's in his account. This is irritating. The amount, currency ADA, from the account of Bob. Okay, and afterwards we are done. So I can let that now go here. Okay, and else now this is now the case that Charlie picked Bob. So we have to do this here, but just with Alice and Bob reversed. So that's Alice, I now say Bob. Let's set Bob, I now say Alice. Okay, and that should be fine. Let's see. Send to simulator. Now I have one additional deadline here. So this is until the time until which until when Alice and Bob need to pay. This is until when Charlie needs to make his decision. And this is before the amount. So this is all fine, I think. So we start the simulation. We already saw what happens if, and again, here, at the moment, this thing is active. So now if Alice makes her, I mean, maybe Alice waits a minute and then makes her deposit. So now we also see that this contract has now reduced. So this trigger happened, Alice made the deposit. So now the active part is this highlighted thing. So now we also saw before, if Bob now doesn't pay, then nothing happens. So it's boring. So let's allow Bob to make his deposit as well. So now the contract has again reduced because now this trigger happened. Bob made the deposit. So now we are here. And now we're waiting for Charlie to make a decision. So if he doesn't make a decision, I mean, we can just let the deadline be reached. Then again, it's boring. Alice and Bob just get their money back. So let's undo this and instead allow him to make a decision. And here, I mean, it's only 1 or 2. So if I, for example, try 3, then the simulator doesn't let me because the choice must be between 1 and 2 because that's how I specified the bounds. So let's first say he picks Alice. So 1. Now the contract is done. And we see Charlie chose value 1 for a winner. Contract pays 200 ADA from Bob to Alice's account. And then contract pays 400 ADA from Alice to Alice's wallet. And if I undo this choice and instead pick 2, then we see the contract pays 200 from Alice to Bob, and then 400 from Bob's account to Bob's wallet. So that works. And that is, I think, already the most important constructs you can do in Marlowe. I mean, I didn't demonstrate all of them, of course, but I think I showed the most important ones. Are there any questions at this point?
No, I think.
Okay, good. Now, just want to show, I mean, here, for example, I mean, we have the whole contract. So let me just, I mean, one thing that's not really nice is that in this, I mean, if we take this game seriously, Alice always has to make the first payment and then Bob. But I mean, of course, I mean, it's completely symmetrical. So in principle, I mean, we want to wait. I mean, it doesn't matter whether Alice or Bob make the first payment. Let me just 1 second. Let me just copy this and just go here. Let me just go here. Just paste that there just for the time being. Sorry. Just as an as a comment. Come back to that in a second. Right. So far, so good. But as you say, I mean, it's not symmetrical because we start waiting for Alice's deposit and then she has made the deposit, wait for Bob. I mean, in principle, we could also, and Bob could start first. That would be nicer. So if we want to do that in Blockly, I mean, in principle, it's simple. I mean, here we have this deposit where we wait for Alice. We just add a second condition in this when. So, right, I mean, in our examples until now, we have always only had 1 trigger, but the when takes a list of triggers. So we can also wait for more than 1 things. So we could just take this condition here that Alice makes a deposit, copy it, paste it, and put it in the same when. So now we have 2. And now in the second one, we could change, I mean, swap Alice and Bob everywhere. But we already, I mean, now we see that we're really getting to the like limits of what Blockly, what can be like nicely done in Blockly. I mean, I love this Blockly editor. I think it's a very cool way to play with very simple Marlowe contracts. I think it's a wonderful way for beginners to learn Marlowe. But I think it's completely impractical to do serious stuff with it because it very quickly gets very like confusing, which is where the other modes of writing Marlowe contracts come in. So if we forget about this now and do Haskell editor, let's say not safe, then in the browser we get this window of a Haskell, I mean, where we can enter a Haskell module, and actually under the hood, what it is, it's just a main program. So that's like a main module, like an executable. And somehow here in the browser, they use a way to like online compile this Haskell. But just, I mean, without looking at the details, just how it what it does. I mean, the main program, I mean, this example, I mean, it has this overloaded strings extension. It's called example. It imports the Marlowe language, which I showed you here. These data types are defined like contract. And then it has here something of type contract. In this case, it's just close. And then all the main program does it prints this contract as JSON. I mean, this print JSON is standard that's probably defined somewhere here in language Marlowe extended v1. So all we get is a JSON, like a printed JSON value that gets printed to the console. And that's then what is taken and, for example, can be sent to the simulator. So, I mean, I could press compile here. And it did compile, I think. No, it's still compiling. I don't know why this silly program takes so long. Okay, but with, yeah. And now I could, for example, send to simulator. And for whatever reason, why this is a bug, this is, I mean, should be this. Why is it still showing the, I mean, I don't know why it's still showing this. I think that's a bug in the playground. Let me just reload everything. Because I did start a new, okay, now it looks better. Right. Yeah, okay, fine. So now it's right. And but so that's nice. But I personally don't, I mean, it's nice because you don't have to install anything. You can just go to the playground and then you can immediately in the browser enter your Haskell code. And that's nice. But I personally don't find it very convenient because, I mean, I can't remember all these data types here. And I would like a Cabal REPL, for example, to inspect the types and know what I can do. Or like my editor support for like tooltips and so on. So therefore, I prefer not to use this, but instead do it locally. And I try to do this in our repo. So let me just, this was a different example. Let me just delete all of that. Because it's not important. And let's just do it what they had, basically. Example. Can remove this. So example contract. So let me just reproduce what they had in the browser. So like this. And now I can actually Cabal REPL X, I think I called it Marlowe Haskell. No, I didn't, it seems. Oh, just Marlowe, sorry. So now I, for example, have my REPL and I can ask for information on contract and then I get that. And here we can also see what it does. So, I mean, if I go out there again and just do Cabal run, I mean, it's just a normal, simple Haskell executable. If I do Cabal run Marlowe, so I execute this program. Then, I mean, this is a bit, I mean, then this is the result. So it just writes this string close. So that's this JSON. Right. And once I have this JSON, I could, for example, deploy it to the Cardano blockchain. So anyway, I prefer, if I want to write my contracts in Haskell, I prefer to do it like this. So let's now take what I had copy pasted earlier. So that was our contract. It just indent. I think that's why it's not valid right now. Okay, now let's open the REPL again. or let's actually execute it. So now, because close was boring. Okay, so now we see like the JSON version of this contract we wrote in Blockly in the playground earlier. Anyway, but now let me do the REPL. Okay, fine. And now, I mean, the advantage, why would I want to do that? I mean, first of all, it's like more compact than these blocks. I have like my tool tips, even though they are not really very helpful at the moment. Just try to reload. I was hoping for some better tool tips. I think when I tried it the other day, I did get better tool tips. Let's see. Or at least I see where it's defined. Anyway. But the main advantage is that now, because I'm in Haskell, I of course have, I mean, all I need to do is construct a value of type contract. But of course, I can use whatever tricks or features Haskell offers to do this. So just as a demonstration, I mean, for example, I have all these roles here, right? And role, so I don't know why somehow something is not working properly. I mean, I think the Haskell language server support is not working. But never mind that now. I mean, I can get away with just using the REPL for this. So let's ask, for example, for information on role. So that gives me a party. So for example, I mean, one simple thing I can do is I can just define helper values. So I can, for example, say Alice, Bob, Charlie, type party, Alice equals role Alice, Bob is Bob, Charlie is Charlie. Okay, should be lowercase, of course. And now I can already make things a bit simpler. Okay, I can do the same for Bob. Okay, and Charlie as well. Here. This is not very impressive, of course, at the moment. Right, then I see, for example, this choice ID thing. Irritating that. So choice ID, it takes the name of the choice and the party and gives me a choice ID. I mean, I'm using that twice, so let me do that. Let's call it CID for choice ID. Charlie. Now things slowly looking up, I think. Use that something else here. Okay, now, I mean, for example, this is Ada. So it is also no. Oh, there is something already, it seems. Let me revert that. So maybe I can just write ADA. So that's already defined there. Okay, fine, even better. So that is good. Right. Now let's see, let's just clean up a bit. These deposits, for example. There. Here can do the same thing. Maybe the payments as well. Okay. Right. And now, of course, I mean, this was now very primitive stuff. I mean, here, for example, I also have code application. So I pay from somebody's, right, I pay to, what was it? That's the payee. So whom do I pay? And no, sorry, this is the payer from which whose account to whom. So I could, for example, do this like, and this, so if I ask for the type of pay, so it takes an account ID. And what's an account ID? Account ID is just another word for party. So, so for example, I could do pay. So from account ID, actually it's two parties in my case. Party contract. So pay from to, and that's basically just copy this. So from to. So now I can replace this whole thing with from Bob to Alice. Alice Bob. Okay, that's much better already. And now, I mean, this I can make a little bit cleaner. Okay. Right. I mean, now it's already much easier to read, but it's still the same thing. And originally I said I want to like make it symmetric so that Alice doesn't have to start, but that instead Bob can also start. So I can abstract away from, I mean, this whole part. So what's the case? Second. So case takes an action and a contract, and so action is, I'm sorry, no, I mean the case. It's a list of cases. So I can abstract away this whole case thing. So let me, what do I call it? A deposit, for example. And it depends on who pays first. So in this case, it was Alice and then Bob. So let's just abstract those two. So party, and then make a case out of this. So deposit, let's call it first and second. And now let me copy this whole thing, the whole case. Of course, at the moment, it's a list of cases. I'm aware of that. So let's remove this. And now So Alice is first, second. And this actually can stay as is. That doesn't matter who paid first and who paid second. So, okay. And now I have this, so I can replace this whole thing with case Alice Bob. And now, of course, I can also add the other case that Bob pays first. Case Bob Alice. Why is this? Oh yeah, cases. Sorry, I called it deposit. Cases, of course, a keyword. Sorry about that. Like this. Right. Okay. And now I can see whether I made a mistake. And I can also like look at example. So this is now more complicated than before, I hope. Because it should now have both these deposits. And now, of course, I can also copy this whole thing. Let me just go back to the playground. So here, let me delete the example they have, and let me copy mine. The problem, no problem. There are no problems, they're just challenges. So. Right, so I just copy pasted everything. And now I hope that it still compiles, but it should. Yeah, good. And now if I send it to simulator, and now we see it's like much bigger. So the point I'm trying to make here is you can use, I mean, in the end, you need a contract, which I have. I mean, it's this example. It's a value of type contract. But how you construct this value, this Haskell value, I mean, you can do whatever you like in Haskell. In particular, you can define helper functions like I did here. So I use like features of Haskell, some arbitrary helper functions. It doesn't matter. In the end, I just need a value of type contract. And I have that now. This is this value that I now constructed. And now it should have whatever, 150 ADA maybe. So now we see that we have these two triggers. So now Alice, as before, can make the first payment, but Bob can also make the first payment. So if, for example, Bob makes the first payment, so now it's Alice's turn. So she can do it. And let's say Charlie picks Bob. And in the end, Bob gets the money. So that's one reason why you would want to not use Blockly or something, but instead use a proper programming language to construct these contracts. Because then you have all the features of the programming language at your disposal, and you can do like abstractions. You can extract helper functions like I did here with this deposit function, for example, to make life simpler. And then there's also something that, I mean, where you really need to do it like this. I mean, one thing, I mean, one of the disadvantages with Marlowe it being so simple is, I mean, it's really very, I mean, not only is it not Turing complete, it's very far away from being Turing complete. So it's really rigid. I mean, you know everything about the contract before you execute it. In particular, I mean, all the values and the deadlines are like hard-coded. But for that, there is this template mechanism. So we use this payment deadline and choice deadline. But what's also rigid is the parties, the participants. So in this case, there are exactly two, Alice and Bob, and this also can't be changed. And I think it's not possible to use templates for the participants. But even if it was, I mean, in a sense, these role names are like templates because whoever owns the corresponding NFT can play that role. But what if I wanted to do the same thing now but for 3 people or 10 people. And that's really impossible to do in Blockly, or like, I mean, because you can't do the number of people dynamic in Marlowe. Marlowe simply doesn't have a concept of that. I mean, Marlowe just always, a Marlowe contract always has a fixed finite number of participants. But of course, using Haskell or a programming language, it's easy to do this, or relatively easy. So as another example, let's try to generalize to arbitrary to arbitrary participants. And so let's see. So first of all, yeah, let's do that. So the idea is I want to write something, I don't know, let's call it game or example, whatever. I mean, example, let me just, because I think it's easier if I have this old contract to steal syntax from. So now the idea is I want to write something like example that gets a list of parties and gives me a contract. And then I want to be able to, let's say, a list of parties and one party, which is the person or the entity that makes the decision. So I want to be able to reproduce the original one with role Alice. So my original example would be this one. Role Bob are the 2 parties, the participants, and the Charlie is the one that makes the decisions. So this is the goal now. For every single like actual instance of the contract that runs on the blockchain, I must pick parameters. I must pick a fixed number of participants. But at least, I mean, if I want to do today, I want to do this with 2 people and tomorrow with 10. I don't want to each time like write a completely new contract from scratch. So the idea is I write a Haskell function that can do that for me. So it's like it's again a bit like meta programming, except that this time we don't use Haskell to write Haskell. We use Haskell to write a contract. And of course, a contract is just a Haskell data type. So that's just a plain vanilla Haskell function. Right, let's do this. So, of course, there are, okay, fine. So how does it work? I mean, let's see. I mean, we can basically use the one we had for 2 people as a guiding example. So let's call that parties. And let's call that whatever, I don't know, Oracle. So I mean, the general structure is like this, of course. It's a when, then we do something here, and we have that. So I can actually copy paste this. So what we do here, we don't yet know. So let me just put an empty list there. Okay, but this is the general structure of the contract we want. So now here we need all these triggers. So for each participant, we need something like this deposit. Except that now it's not just first and second, now it's more complicated because we have more people. Right. So basically what we need here is, so we must loop over all our parties, and then, so in this example, the list is Alice and Bob. So we want to loop over this list and create one case where Alice is first and one case is where Bob is first. So I can again call that deposit, maybe. So I map deposit over the list of parties. And of course, deposit needs to be written. And let me just think for a second. No, I think this is not good enough because I need to do that recursively as well. Because in this case, I mean, there were only 2 deposits, but if I have 10 participants, it will of course be very deeply nested. So what instead I want is I want to call deposit with like the person that's supposed to make the deposit and everybody else. So let me just pause for a second and just write another helper function that takes a list and gives me, let me just think. Right. What I want is that deposit has the following signature. So it takes the party that's supposed to make the first deposit and then a list of remaining parties that after that have to make a deposit, and then gives me a case. Deposit undefined. And now, of course, the signature here is not correct anymore because now deposit takes 2. So I map which function. So given the party that makes the first deposit, I call my helper function deposit, and the rest is all other parties of all the parties. Okay. Okay, so at the top level, so this helper function gets a party that is supposed to make the first deposit and a list of all remaining parties, and then is supposed to give me this case where this party makes the first deposit and then the others are handled. Okay, and I call that at the top level. So I loop over all the parties. Each of those parties, I create a case with my deposit helper function where P is the first one. And the others are everybody else. So everybody that's not P. Okay, so now I can concentrate on implementing this. And I can basically sort of try to copy this. So let me do this. Of course, it's not undefined. And now I have P and PS. So P is the one that is supposed to make the deposit into his or her own account. Okay, and now this when is what happens afterwards. And that depends. It depends on whether somebody else still has to make a deposit or not. So the second case is, so this when is, so it depends. So case PS off. And there are 2 cases. It's the empty list. So I'm done, or it's not. So I have like a QS left. Okay, so in this case, I can recursively call deposit. So I just do so I can basically do the same that I did here. So this is now a bit ugly, but nevertheless works. Sorry, let me just call this, give this a name. So this is the non-empty case. In that case, I will basically do the same did here. So this is really a bit ugly. I'm now wondering whether I probably should have done that differently. But anyway, can clean that up later. So I basically copy this here. Because now I have code duplication. This is, must comment that. Right. Okay, so now it's not parties anymore, it's my queues. Okay, so this takes now care of recursively if there are more people that still need to do payment. I mean, I basically did the same I did here, and this is ugly and one could do it nicer, but maybe we can do that later. It also doesn't matter. So this is now the case where the last people has made a deposit, and now we must do the choice and the rest. So this is now this here, or rather, until here. So let me copy that in here. So the undefined case. Okay, didn't need the parentheses. Okay, so the CID is, I can just copy that from here, define it here somewhere. And now it's not, oh, sorry, I should probably put it here. Because now it's not Charlie any longer, it's what I called Oracle, so it's configurable. So that's fine. Now we see the bound. It used to be 1 and 2, but now, of course, it instead of 2, it must be the number of people in the party. So length parties. Why is this giving me pain? Okay, because it expects an integer and this is an int. So it's just from 2 to integer, for example. Okay. And now, of course, this here gets more complicated because now there's not just 2 cases, Alice or Bob. There are like potentially 10 cases or arbitrary many cases. So I must somehow also abstract that away. Right. So I need a helper function for this as well. So let's call it payment or something. So payment, let's see what the 1 is. It's an integer, okay. Right, and somehow I need to know which integer, which choice corresponds to which party. So let's take a list of pairs of parties and integers. So this is the potential still possible choices that can be made. And the whole thing is a contract. So which I will put here. So this is now still to be replaced. So let me just fill that in later. So I replace this if. So instead of this if, let me comment that out. I now call this payment. Payment. And what's this list? So I can get that with zipping all the parties with the list starting at 1. Okay. So now everything compiles again. Okay, now I must do this. And I mean, if it's the empty list, then I'm basically done. There's nothing I can do. So if it's the empty list, then it's just close. And if it's not the empty list, so I have a party and corresponding integer and a rest. Okay, and now I can finally copy this thing here. Just indent. So if, right. So if the choice value, and now it's not constant 1, it's constant n. Okay, the payments, I have to do something. But if not, I can recursively call the payment function on XS. So payment XS. Okay. So now the part I still have to figure out is, so okay, fine. If the Oracle chose party P, how do we do the payments? So now basically we need to make a payment from everybody else that didn't win to him. So so maybe I shouldn't have called that payment. Maybe I should have called it something else. Maybe choice. Choice. Okay, so now all that's remaining is I must somehow do these payments. So pay, for example, party is the one that won. I must make a contract out of that. And let's say all the people that need to pay. So the idea of pay is create a contract where everybody in this list pays to that party. And I call this function here. So pay, so who is the winner? That's P. Who is everybody else? Well, that's filter not P, all the parties. Right. So now I've reduced my, so I can also delete this stuff here. And basically everything is now good, I think. All right. So now all that's remaining is I must make these payments. Okay. And now I forgot how to do this. Let's check again. So it takes the account ID from where these payments are made and to whom they are made. Payee is to whom, and that can be account or party. So in our case, it doesn't really matter whether I can, for example, do it to the winner's internal account. Right. So if no payments has to be made, I'm done. So I can close. So and if there is at least one party queue that still needs to do a payment, then I do a pay. Okay, this is from whom. So account ID was just a synonym for party. So that's Q. Now to whom. So that's, let's say, account P. Now token, that's ADA. Value is this, what was it? Somewhere in the deposits. This is this constant param amount. And what to do next. And next we recursively call pay for the same winner, but with the remaining pay people that still have to pay. And I think now everything compiles, I hope. Let's reload. Okay. And now, first of all, I mean, it's not very long. And if I do like that, I should get the original one back. So let me just go back to edit source, delete everything here under the main program, by actually including the main program. And now let me copy everything. Copy. paste. Let's hope it works.
Yes, sure.
Okay, at least it's green. So this should now be exactly what I had before, but now, of course, in this general form. So times are, I mean, a bit silly now. Let's do 30, 35. Okay, so this is hopefully exactly as before. Let's say Bob starts. Now Alice is left. Alice starts. He picks, Charlie picks 1, and Alice gets the money. So far, so good. So, but now I can like easily change the parties. So for example, I can say I want 4 participants: Alice, Bob, Charlie, and I don't know what one used for D, Doris, Dora, Delta. And the oracle I call, I don't know, oracle. And now if I compile again, hopefully that also works. Okay. And now if we look at the contract, we see nothing, because I think this is again this bug that it didn't refresh. So let me reload. Now we see that it's really long now. So long that this almost crashes. So it has like now 3,684 rows. Because basically Marlowe has no abstractions. So every single potential path, I mean, order in which people now make their deposits is a different branch in this code here now. But it seems to have worked. At least there was a valid. So let's try the simulation. Okay, now we see, I mean, I now had 4 parties that play that game. So now I have an action available for all 4 of them. So for example, oh yeah, but I didn't set the value. So let's set it to whatever, 100 ADA. So let's say Charlie starts, and now correctly, the contract has reduced now to this case where Charlie made the first deposit, and now those 3 are left. So let's say Alice goes next. So now the contract again has reduced to where Bob and Delta are left. Let's say Delta goes next. And now we're waiting for Bob's deposit. And let's say Bob makes it. And now hopefully the oracle should accept from 1 to 4. Yeah. And let's say it picks 3, Charlie. And we see contract pays 100 from Alice to Charlie, 100 from Bob to Charlie, 100 from Delta to Charlie, and then 400 from Charlie to Charlie. So I think it works. And of course, the specific example is not important. I mean, the point I'm trying to make here is that using Haskell, for example, to like write contracts for you. I mean, all this does is just a normal Haskell function that constructs. I mean, I can also run it in GHCI, of course. I mean, I can just do main. Oh, sorry, example. What was it? I think I can just use strings, because I think party implements is string. So I don't have to write this row thing. Delta, I think. Maybe wrong though. Yes. No, maybe I must set overloaded strings here in the Apple. Yes. So this like 3,000 lines long Marlowe contract with just a Haskell value. It's just a Haskell value of type contract, right? It's just of type contract. So I mean, this is just like week 1 Haskell, just working with algebraic data types and constructing values of them. But you can also look at it as meta programming, where you use the Haskell programming language to write a Marlowe contract for you. And as you can see, it can be quite a complex Marlowe contract. Yes, so that is one of the use cases where you definitely wouldn't use Blockly or the Marlowe editor to write it by hand, but would use a programming language to construct the contract for you. And of course, it's like an unrealistic example. Why would anybody do this and trust this Oracle? But you could imagine the Oracle is some lottery thing, for example, where people like the 100 ADA is like the lottery ticket, and then you use some sort of whatever mechanism or a sports bet or something, and then depending on who wins, then I mean one of the people gets all the money. So maybe it's not too unrealistic, right? So that's to show that using Haskell, and of course the same is available for JavaScript. But obviously, after teaching you Haskell for months, I refuse to now show a JavaScript example. But of course, you could do the same thing in JavaScript. So it's also possible to write a JavaScript. I mean, we can at least look at the editor. So then it's like this. So it imports certain stuff, and then you must write a function. So it's more like TypeScript, actually, I find. So maybe JS editor is a misnomer. I think it's TypeScript.
Yes, but he's better in Haskell, Lars.
Yeah, it's better than JavaScript, but not as good as Haskell. But yeah, you could also do the same in TypeScript. And I think the editor also has, yeah, it has certain support for these things. So it's like tooltips and like what's it called? Context sensitive help. Anyway, so yeah, so that's the basic idea. So to recap, maybe I don't know, we can do another example. We still have time, or maybe there are questions. But just to recap, so and then we will go, I mean, how that actually looks, or what that looks like on the blockchain in the next lecture. But so the idea is we have like smart contracts that are supposed to get rid of the ambiguity inherent in natural languages like English. So everything is formalized, and it's got inspired by this formalization by Simon Peyton-Jones and his co-authors for like real-world financial contracts, adapted to the blockchain. So certain things like that, for example, that you can't force anybody to do anything are taken into account. But then we end up with this very simple DLL, domain-specific language, and it has been carefully designed to be statically checkable. And in particular, it's not incomplete. So you can't do arbitrary things. You can't like do crypto kitties or something like that. But what you can do is financial contracts. And those, because of the way it has been designed, can be statically analyzed. So it's possible to write tools that automatically detect if you if there are certain problems with your contract. For example, that upon hitting close, there's still money left in one of the internal accounts. And I mean, there are these 3 example checks implemented in the playground, but you could imagine that you can write other example checks as well. So that's maybe one thing we could still do. But anyway, so that's the design decision that Marlowe made. So it's extremely simple, not Turing complete, can only do certain things, specialized to financial contracts. But on the positive side, that allows us to write powerful and static analysis tools for Marlowe contracts to make it possible to basically analyze before you execute them what can and cannot happen. And then you can create those contracts in various different ways. So for beginners to play with it, this Blockly is nice, where you just need the mouse, more or less. And then you can do it also, like if you want to do it in earnest, you can use Haskell, for example, to generate values of type contract. And then because I mean, in the end, only the value matters, the JSON encoding of the value. So that's what you need to actually deploy it on the blockchain. But you are totally unrestricted how you get to that JSON value. So you can use all the Haskell features you want to come up with this value of type contract. And then you, as we will see on Thursday, then what you do once you have that contract, how you actually get it on the blockchain. But that's basically the idea. And I should, before I forget that, I should mention that Marlowe, I mean, at the moment we only have Plutus and Marlowe on Cardano, but Marlowe was always meant more as a proof of concept. So just to show that it's possible to have like specialized domain-specific languages that are limited, much more limited than Plutus, but can do one thing very well, like financial contracts, and that it's possible to implement a DSL like that on the Cardano blockchain. So if there are other domains, then it would be possible to create other smart contract languages similar to Marlowe that are specialized to other domains than finance. Right. So that's that. Are there any questions at this point?
I think so far there are no questions. Okay. One more example, please. Say Samsung.
Yes, sure. Can you think of anything interesting, Karina? I mean, I always like auctions, but yeah, sorry, go ahead.
Yeah. I think it's a good, but this.
Right. Yes. The only problem with auctions is, I mean, that's one of the limitations of, I mean, a normal auction is basically can run a long time, right? It can, because as long as somebody is willing to make a higher bid, it goes on. And in Marlowe, you can't have it. I mean, Marlowe doesn't have loops or anything. So, and in particular, we know that it's always possible to statically look at a Marlowe contract and decide if it, I mean, when it will, how long it will run at the most. So it's from that alone, you already know you can't implement like a traditional English auction just like that. But one thing we can do, I forgot. Yeah, go ahead.
So Anderson said there is a question for him, the one on deploying on testnet. What is the question? Okay, sorry. I forgot, sorry. There are other questions, Lars. Kim asked, is there a way to deploy to a testnet directly from Marlowe?
Yes, there is. And we will talk about that on Thursday. So, I mean, basically today I wanted to explain the Marlowe language itself and the reason why it has been designed like this. And now that we basically, so now the question of course is what, once we have a contract, a Marlowe contract, what do we do with it? And we want to talk about that on Thursday. So in particular, you can take the JSON that like this Haskell program produces and deploy it on, for example, the testnet, and then run it and execute it. And of course, also on mainnet. But we don't want to do that for obvious reasons because we don't want to use our own money for this. But yes, you can take a contract like this. I mean, there's this, sorry. Somewhere here, there is always the option to, I did this horrible. I should have saved maybe. Anyway, I mean, there's this view as Marlowe and send to a simulator. And there's this download as JSON. So I can download these contracts. That was still the nice one, the long one, because of this bug. So I can download this as JSON, and then I have it as a file. And using this file, as we will see on Thursday, it's then possible to deploy it on Marlowe. Sorry, not on Marlowe. On the blockchain, on the testnet. Does that answer the question?
Yes. Yes. Thanks.
Okay, example. I mean, one example is always this escrow thing, but I have seen that so many times that I find it boring. Just not sure whether in 20 minutes I can do the auction. I suppose I can, why not?
Yeah, or choose someone of the examples that
I always
really
have all
exists
the,
in the playground, maybe.
I always find them so boring, but
Yeah, yeah, but it's only an example.
true. Uh, okay, escrow is maybe nicer.
Yes, I think it's good signs.
Okay, fine. Let's look at the very first example. Okay, let's first just see how it works in the simulator. Okay, so it has an initial time, then it has deadlines, payment deadline, complaint response deadline, and mediation deadline, and the price. So let's first, before we look at the contract, just let's say it's 100 ADA, and let's just see what we can do. So first, the buyer can, I mean, the idea is you want to buy something of somebody you don't trust. So there are like two different, I mean, lots of different things that, I mean, the buyer wants to buy something from the seller. Um, and of course, if they don't trust each other, I mean, the buyer, if he sends the money, then the buyer can't be sure that the seller will actually send him whatever he bought. Like, I don't know, what can you buy for 100? A book. So the buyer wants to buy a book from the seller. So the idea is the buyer sends the money to the seller and the seller sends him the book. Now, of course, the buyer doesn't know whether the seller will actually send him the book. Or if he sends it to him, he can't be sure that the book is like in good condition and so on. So there's this idea of escrow, where instead of sending it to the seller directly, the money, and then hoping for the best, he sends it into a Marlowe contract. So he sends it into this. So if he doesn't, then nothing happens, of course. But let's say he makes the payment into this seller's um, debt account. So now the seller is supposed to send the book. And if he does and the book is fine, then the buyer would make this choice here. So here it's done differently. So here are two choices with only one value each. So that's a bit nicer. I could also have done it like that. So instead of just having one choice with two possible values, here it's two choices with only one possible value each. So the idea is that if you can, I mean, make the one choice or the other choice, and right. So if everything is all right, so if the buyer chooses this or doesn't do anything, then that's it. I mean, then the seller just gets the 100 ADA and everything. And now it's 100 million ADA, so it's an expensive book. So it's probably somewhere multiplied by a million or whatever. Anyway, let's not worry about that. So, but let's say the seller, I mean, the buyer sent the ADA, but the seller doesn't send the book. He can make this choice report problem. So now the seller can choose. So he can say, yes, my bad, I didn't send the book, and can confirm that there was a problem, in which case the contract ends and the buyer got his money back. So we see a buyer chose value 1, record problem. So then the contract sends the 100 million ADA from the seller account to the buyer account. Oh, okay, it's different here. So at the moment there's a problem reported, this payment happens, but I mean that's not strictly necessary. But anyway, so the seller confirms, in which case the buyer gets his money back. But now if the seller does say, but I did send the book, so he disputes that there's a problem. So now this mediator, a third party, enters. And now the mediator can decide. So if the mediator believes the buyer and says, you never sent the book, he can decide for the buyer, in which case the buyer gets it. But if the mediator says, no, the seller is right, he did send the book, then the seller gets it. And if the mediator doesn't do anything, then in this case, the buyer gets his money back. So in this case, like the buyer has an advantage somehow. But anyway, that's how this works. And I mean, this is it in Blockly. So it's not too bad, actually. So we see, first we wait for the deposit of the buyer, and then the buyer can make this choice. So if everything is all right, everything ends. And if there's a problem, then it becomes interesting. So then the money gets shifted internally. Now the seller can confirm, in which case everything stops. But if the seller disputes, then we wait for the mediator who can dismiss the claim or confirm the problem. And yes, so that's actually quite a nice example. So that's for that's this escrow example. So instead of, it's a bit like Amazon or eBay or so. You have the option to complain, and then eBay or Amazon like look at the case and decide. So you can do that with Marlowe relatively easily, as you see here. Of course, in reality, you probably would want to somehow incentivize the mediator to actually mediate. So no idea, but I mean, somewhat realistic example. I mean, there are more examples. Here's escrow with, okay. So because, I mean, here in this first example, I mean, there's somehow like financial incentive for the buyer to always complain that there was an issue, because, I mean, he can't lose anything. I mean, the worst case, he loses the mediation, but if he's lucky and the mediator doesn't decide, or if the seller is on vacation and doesn't check whatever, then the buyer, when he complains, gets the money back. So somehow it's a bit unfair. The buyer has an advantage, and it's incentivized to always always complain. And so they have this other example here, where they first have to do a collateral payment, but I have to set the collateral. So for example, I can set the collateral to 10 ADA, and the price, let's now do 100. So now the idea is first they have to deposit these 10 ADA before anything else happens. So let's say the seller does it, the buyer does it. So now into their own internal accounts. And now what happened before happens. But now if the buyer reports a problem, okay, fine, so far so good, nothing more happens. And if the seller confirms the problem, okay, then I mean the buyer gets his collateral back, fine. But if the seller disputes, then we see here that the contract pays 10 ADA from this, so the collateral to some address test one, and same for buyer. So the idea you must think of here that address test one is some unreachable address where it's impossible to retrieve money from ever again. So that's easily doable on blockchains, including Cardano. I mean, you could just, if you a random address, then nobody will be able to retrieve money from that, because in order to retrieve money, you would need the private key belonging to that. And if you randomly thought of an address, it's very unlikely that anybody will be able to guess the private key. Or you could also use a smart contract for that just never pays anything out of it again. Not the Marlowe contract though, because Marlowe contracts are designed in a way that money can never be stuck in them forever. But anyway, yeah, that's the idea of this one. And that's also, okay. And this is probably a bit more complex, but still not too bad. I mean, like 2 blockly screens. So you can see that, I mean, already that you can do quite complicated things. So here there's also already a lot of things that can happen. And lots of steps with deposits and payments and mediations and so on. So but I think it's quite nice. And of course, you could also do this differently, that instead of, I mean, the 10 ADA being burned, you could also use the 10 ADA of each party to go to the mediator. I mean, that would pay the mediator, and it would have the same effect that the parties try to collaborate, because if they don't, if they need the mediator, then both of them lose at least some money, maybe the collateral. So yeah, I think that's also quite a good example. Are there more questions?
Let me see. No, no, so far there are no
Okay.
questions.
Maybe I should also mention that, I mean, I said that that Marlowe is just a Haskell type. So Marlowe contract is just a value of that type. But that's like only partially true. I mean, it's true enough, but when it actually runs on the blockchain, then, I mean, like fundamentally on Cardano, there's only Plutos. So every smart contract is a Pluto smart contract. Well, that's also not, I mean, there's so-called native scripts, but that's like a different story. So in principle, there's only Plutos. So what, I mean, Marlowe is implemented on top of Plutos. So there is like a Plutos smart contract that acts as a Marlowe interpreter. So on the blockchain, Marlowe is, Marlowe is not a Haskell data type. It's more like a Plutos data type. But same idea. So, yeah, and what I also should say, I mean, Marlowe is limited in certain, like with this, you only have like, you can't do a proper auction because the, you can't have like something that runs forever or for an indeterminate amount of time, because Marlowe contracts always have like a specific finite lifetime. So probably for a real world case, Marlowe will never be enough. So the idea is that you mix Plutos on Marlowe somehow. So you use Plutos on the, it's a bit like IO in Haskell. So you, I mean, in Haskell, you need some IO actions, but then you try to write as much as possible in Haskell. And the idea or the vision behind Marlowe is that you do what is necessary, what needs to be Turing complete-ish in Plutus, and then do like the core financial business logic in Marlowe. And it's possible to mix the two. Right. And maybe, I mean, almost out of time. I just wanted to mention, I mean, I showed you this example before with my expression data type where you can check for exceptions, and you could do exactly this or similar things for this type. I mean, we could easily, I mean, I think I don't have time now to do this. For example, there is this let contract. So you can give a name to a value, and then later in the value type, there's this use value where you can use a variable. So this is like the, a sign in my expression type. And this is like the var in my expression type. And similar to what I did, basically analyze an expression, whether it can have an unused variable, you could do exactly the same and write a function from contract to bool or set of value IDs to check whether a Marlowe contract potentially has like undefined variables. So it's easy to not, I mean, you don't have to be satisfied with the static analysis tools that the playground provides. You can easily write your own static analysis tools if you want to. And the types are really extremely simple. I mean, it's really, in principle, we could have covered Marlowe after the first week or even the first day of, or second day of Haskell. Because it's really, there's nothing, I mean, there are no, okay, fine, there are some. But this has nothing to do with Marlowe directly. So the language itself, I think you wouldn't need any extensions. So it's just vanilla Haskell 98. And also there, I mean, when we talk about Plutus, at least like in the beginning, used quite advanced Haskell if you wanted to work with it. Not Plutus itself, but basically code to interact with Plutus. I mean, the Plutus team used all sorts of advanced Haskell features. Some of those we haven't even talked about in the course yet, or I mean, like type level Haskell and so on. And so Plutus, you need and monads and like complex monads, monad transformers, other types of monads. So lots of advanced techniques. The Marlowe team went a completely different path. So they use only very basic Haskell. So I mean, there's also here somewhere in this repository is an interpreter for Marlowe. So basically you could do the simulator yourself, or I mean, not the graphic one, but I mean, for example, the text-based one would be easy to write it yourself. And I think it doesn't even use monad transformers. So it's all really down to earth, simple, plain Haskell functions. So like philosophically, the teams have implemented those two languages very differently. And Marlowe is really very simple. I mean, it's just these handful of constructors. And yeah, but maybe the last thing I should say is that IOG was, I don't know exactly what the status is there now, but we were collaborating, I think are still collaborating with something called Actis. That's an organization that tried to, independent of blockchain, try to formalize real world financial contracts. So the idea, they wanted to do this, what's called taxonomy, like a classification of financial contracts into a tree of I mean, basically list all the financial contracts that are actually used in the real world and formalize that mathematically. And they claim that they can cover, I forget, but something like 90% or 95% of all real world contracts are actually fit somewhere into their taxonomy. So the huge or vast majority of actual financial contracts are covered by their formalisms. And IOG is or has been collaborating with them to basically take those and convert them to Marlowe. I don't know exact figures, but I mean, again, a large percentage of basically these active contracts can successfully be ported to Marlowe, which means that, I mean, of course, it's always the caveat is what I said before, that like real world financial contracts work differently because you can force people to make payments and you can't on the blockchain. But like taking that into consideration, you can do a lot of like interesting financial things using Marlowe with just these very few basic constructs and then combining them and still keeping the property that everything is just a value of this Haskell type, and you can like easily write analysis tools that look at those values and give you certain properties. For example, that guaranteed that no money is or whatever, that there are no unused variables or I mean, you could in principle do whatever you like. Check that no party will ever get certain money, or that under certain conditions, certain things can't happen. So it's been designed to be easily inspectable, much easier than a program in a general purpose programming language. So yes, I think that's all I want to say, and the time is also up. Of course, if somebody has a question, I'm happy to answer it. And if not, then on Thursday we will, like now, take some of these contracts or write simple new ones, and then actually interact with the real Cardano blockchain, or at least the testnet, and see how you can. I mean, there are also various ways to do that. How we can actually deploy one of those contracts and then like interact with it. Okay.
Okay.
Okay. Then there are no questions. Then thank you very much, and talk to you on Thursday.
Thanks. Bye.
Thanks, Karina. Thanks, everyone. Bye.